It's coming. Okay. So today's lecture is on design of transmission shaft. As I said, it is only mechanical engineers that are designing the transmission shaft. Rest of the faculty in the engineering, in the faculty, the rest of the discipline, the faculty of engineering, will not do it. But whenever it's shaft, it is us. Okay. Why is it us? Because it's moving. Okay. Civil engineers are like us, or we evolved from civil engineering. Okay. But they always do analysis when the structure is static. Okay, in fact, civil engineering is the first discipline in engineering. Okay, so it's static, right? The only thing that the civil engineer does that is dynamic is earthquake. Okay, yeah, earthquake design. That's them. Mechanical engineer, we can do not just static, but also dynamics. Okay, things that are what rotating. Okay, so as I mentioned, design of transmission shaft, okay, usually are done by mechanical engineers. Okay, very seldom what you call civil engineers are involved. Material science, maybe sometimes, okay, they have to know. Okay, right. So transmit. By the way, I have uploaded images on Avenue to Learn on the content module, and its figures. So there are these figures that that I'll be using a lot. Okay, so go to Avenue to Learn, download them. Okay, you can click onto the announcement, the image will come out. Okay, and I'll use these diagrams quite a bit. Okay, so now let's go. So before we design, we need to see how we analyze first. Okay, how are we gonna? So this is the time. So yesterday I went through 2D mold circuit. So this is one time that we're going to apply 2D mold circuit. Okay, when we design transmission shaft. When transmission shaft, okay, you can apply just 2D mold circuit. Okay, so now let's look at an element. Okay, let's look at an element. Okay, let's look at an element. Okay, so let's look. So when we have an element, so I'll draw an element out. Okay, so this element is on a shaft. All right, so I'll draw our axis. So this is my x, and this is my z-axis. Okay, element on a shaft. All right, so the overview. So in 3D, I'm going to sketch this in 3D. So this is x, this is y, and this is my z. Okay, so we have a shaft. All right, so this is our shaft, and I'm going to drop the centroid. Okay, so this is our centroid. Now, any question, please stop me, okay, at any time. So looking at the orientation on the view of the element, I'll just do a quick sketch. This is where our element is. It's on the surface of the shaft. Okay, it's on the surface of the shaft. Right, so now you can visualize this now. So on the shaft, we are going to see stresses. Okay, this is just an example. Okay, so we can see stresses. You can have either compressive or tensile stresses. Okay, in the x direction, and all shaft undergo torsion, and torsion. What we get from torsion is we have shear. Okay, and this is our shear. Our plane is intersecting the x-axis. Okay, so shear. Sorry, so this is shear x. The plane intersecting the axis is x, and the direction of the shear is z. Okay, so this shear z x. Okay, now, so when our stress is loaded in this way, okay, so we have a load coming in this direction. Okay, so this is our axial load, right? Our axial load. Then we can have a point load, okay, coming vertically down, and that is our Py. And we can have another force coming in this way, that is our Pz. And then to make matter worse, or in reality, okay, we will have a torsion. Okay, so this will be torque in the x direction. Okay, so now let's do a recap. Okay, let's do a recap. So to analyze stress x, as you all know now, very familiar to all of you, we will have stress x. Okay, we have stress x is equal to Py divided by A, right? So that's due to the axial force. Then we also have our hold on. We also have our, yes, corner. This is week 11. Okay. Then we also have our plus. Okay. So we will have our plus by moment about z over izz multiplied by, so if it's z multiplied by y plus by moment about y over Iyy multiplied by z. Okay, so this is the load, or this is the stress. Okay, that is working on stress x direction.
Professor,
Yes.
shouldn't it be px
Oh
in the
yeah,
stress x equation?
you're right.
Also in the diagram, I think you also labeled pz as px.
Yeah, I'm sleeping today. Where are you? Connor again. Connor, you're going to be very drunk after this class, okay?
It'll be good
Okay.
for after finals. Thanks.
Px over A, okay? I still owe people money. I'm not paid yet, okay? Okay, now, so we know we know that, okay, that is induced by our this is induced due to axial loading. So this is under axial. Okay, and over here, this term is our due to bending moment. Then the next one that we have, okay, the next one we have will be our shear in the, or the shearing stress. Okay, induced by torsion and shear force. Okay. Now, before I go on, if we look at stress in the x direction, okay, and if we have this, if I sketch the distribution, okay, so this is my stress in the x direction, okay, so this is my radius, okay, the wider the radius, right, so this is our radius, and we know, right, we know that our distribution, okay, will look something like this. Okay, something like this. Okay, so what to take note is when radius is maximum, right, when the radius is maximum, our stresses are also at the maximum. Okay, so now when we look at our shearing stress, there are two. One is due to torsion and one is due to shear force. So the torsion one, okay, so the torsion one is shear xz is equal to shear zx, and this one is equal to tx multiplied by radius is divided by second polar moment of area, right? So the distribution of the shear stress, okay, the distribution of the shear stress look like this now. Okay, so this is our stress. This is our shear, and this is our radius. Right, this is our radius, and the distribution now looks like this. Okay, I think I showed you guys this before. Right. So again, tau max occur at R max. Okay, radius max, and the one above, right? The one above is we also have stress X max. Okay, occurs at R max. Okay, and then another one in contributing to the shear, right? Is shear xy or xz equal to shear. Oi, sleeping Eugene. Okay, it's equal to shear zx. This one is equal to v. It can be, okay, so it can be both ways. Okay, so it can be vy over izz, right? Qz divided by thickness. Okay, and okay, you can have both, right? You can have vz over iyy qy divided by t. So for this case, the trend is not the same anymore. What trend do I mean is where the maximum occur. Okay, so we have this. Okay, then this is our shear, right? So we know the distribution now looks like this, and this is our can be y or radius. Okay, can still be radius based. Okay, so our distribution is different now. Our distribution looks like this. Okay, so this is where our tau max is. Okay, so i.e. tau max occurs when radius is equal to 0, right? So if we have in context, if we have, I'm going to shift this a bit. Okay, all right, so this is our shaft, right? This is our shaft, right? So if it's due to if it's due to vy, right, over here the shear will be 0, shear will be max, and coming down to here is 0. Okay, and then vy again. Okay, now can you see what my issue is? Can anyone tell me what is my issue or what is my problem? Anyone? What is the similarity between stress X due to axial load and bending moment and the shearing stress induced by the torsion compared to the shear force? Anyone?
The first two are 0 at the centroid, but the last one is max at the centroid.
Yeah. Okay. Mustafa, you're right. I should not draw them as SZ yet. Okay. I'm just doing, this is just, I think what I'll do, I just put shear down here. Okay. I just put shear down here. Right. So now, Miriam is absolutely right. Okay. The problem is the maximum occur at different location in the shearing stress induced by the shear force. Okay. Now, later on we'll prove this. Okay. And you guys will say, hallelujah. What do I mean? Okay. The shearing stress Okay, induced or generated